Hello and welcome. Dear students, today we are going to discuss an important topic, that is catchment runoff and river discharge. In this lecture, we will be discussing the concept of runoff, its generation and measurement of river discharge. Catchment or watershed is an area that is drained by a river and its tributaries. The precipitation over this area is distributed into different components. Runoff is the volume of water that flows over the surface after the soils and surface depressions are saturated. The runoff water from all parts of the watershed reach a stream and becomes part of its natural flow. The magnitude of water flowing through a river at a particular place and time is called discharge. The continuous and exact data of this volume is measured using several methods. The data has huge significance in hydrological studies and water resource management. This academic module makes students understand how the rainfall becomes runoff and what are the factors that affect its volume. It also gives an overview of the methods that are used to measure the river discharge data. The lecture also provides an understanding of its significance and how has the discharge of some Indian rivers changed in past decades. Now, let us discuss runoff generation in a catchment. The volume of water that flows over the surface of earth in a watershed is called a runoff. After a rainfall event, it gets distributed into different components such as evapotranspiration, interception flow, soil storage, through flow and runoff. The runoff is the volume of water that is generated after the soils and surface depressions are saturated. It is also called as saturation excess overland flow. Robert E. Houghton, an engineer by profession, first made detailed studies of this phenomena in 1933. Thus, it is also called as Houghtonian flow or direct runoff. Runoff can be from rainfall, snowfall or irrigation and flows over land into streams, rivers and drains. The volume of runoff water from all sides of a watershed ultimately reach a stream and become part of its flow. This is called as stream flow or discharge. Discharge, denoted by Q, is the volume of water that flows from a specific cross section of a river channel in a given time period. It is defined as the volumetric flow rate of water passing a river cross section per unit of time. It has typical units of liters per minute. In case of big rivers, it is measured in cubic meters per second or cumex. Other commonly used ways are cubic feet per second or gallons per day. The graph that plots the volume of flow in y-axis against the time in the x-axis is called a hydrograph. The shape of hydrograph determines the nature of runoff in a watershed. It has huge significance in watershed management. The shape is defined by several properties, specifically its lag time, which denotes a delay in time between peak rainfall and peak discharge. Other parameters include the magnitude of peak discharge, the concentration time, the shape and slope of limbs. A storm hydrograph is simply a discharge graph of a stream generated by a single rainfall event. It visualizes how a specific river catchment responds to rainfall input over time. It serves as a vital diagnostic tool in hydrology. Now, let us discuss the factors affecting runoff generation. Runoff generation is a complex process. Several factors affect the runoff generation in a watershed, including climate and watershed characteristics. The amount and duration of runoff depends on climate and its pattern. In arid and semi-arid watersheds like Rajasthan, the runoff will be less compared to the humid watersheds of Himalayas. The runoff in monsoon-dominated areas of southern India will be different than the Himalayan climates. Furthermore, the type of precipitation also affects runoff generation. In the Himalayan watersheds, snowfall delays runoff until the melt season. Geology also dictates runoff mechanisms. Impermeable rocks such as basalt of the Deccan Traps resist infiltration. This forces water to flow rapidly as surface runoff. If the overlying soils are saturated, it amplifies the runoff generation. This is commonly observed during the active phases of the monsoon. This is the reason that in such watersheds, subsequent rainstorms cause immediate rises in river levels. The geometry of a basin also determines the runoff flow. In circular catchments, runoff from various points reaches the main channel simultaneously. This causes a rapid high peak flow, often termed as flashy hydrograph. This is mainly seen in the Himalayan rivers, which have steep gradients and circular shape. Conversely, in elongated basins, flow takes time to reach a river channel, causing a low peak. It also depends on the runoff contributing area in a watershed. For example, in urbanized watersheds, runoff will be very high, while in the forest watersheds of same size, the runoff amount will be less. Forests increase interception and transpiration and extend the lag time in a hydrograph. Similarly, low infiltration capacities enhance the runoff compared to those where infiltration is low, like in barren or urban watersheds. When infiltration is high, some parts of it flow subsurface laterally along the slope and is called interflow. It also reaches the surface and some places and becomes part of runoff. In Indian conditions, there are wet and dry spells during which soils remain either fully saturated or either dry. These conditions are called antecedent moisture conditions or AMC. The soil moisture data of these spells is a vital parameter in modeling the runoff and discharge in watersheds. Runoff also depends on soil types. In case of black cotton soils of Maharashtra and crusted soils like in Andhra Pradesh, runoff will be high. Low infiltration capacity in these soils forces rapid overland flow. Now, let us discuss discharge measurements. The continuous and accurate measurement of river discharge is a foundation of hydrological studies. It is measured using two common methods. First is the stage data. Stage refers to the elevation of the water surface in a river above a fixed reference point or datum. The datum is usually the river bed surface. Stage data is most easily and continuously monitored hydraulic parameter. At any location in a river, stage is commonly measured using staff gauges, float-based recorders, pressure sensors or radar and acoustic instruments. However, the measurement is difficult due to rapid fluctuations of water during floods and dry seasons. In India, the Central Water Commission or Central Water CWC operates thousands of gauging stations installed at rivers like the Indus, Jhelum, Ganga, Brahmaputra, Godavari and Krishna. Now, discharge measurement. Discharge is the total volume of water that flows through a river. the most widely used method is the velocity area approach. It is based on the fundamental relationship of multiplying the area of river cross section and the velocity of flowing water. Thus, discharge or Q is equal to A multiplied by V. The river cross section at the measuring site is divided into several vertical segments from surface to bottom. This is because the water speed varies across a river channel. The flow velocity in each segment is measured using different techniques. A stopwatch is a common instrument to estimate the velocity of flowing water. To measure the river discharge, hydrologists take the cross-sectional area A and average velocity V. The equation is solved for each segment to calculate the discharge as Qi is equal to Ai into Vi. The total discharge is the sum of all individual segments at that point and is given as Q is equal to Q1 plus Q2 plus Qn. Nowadays, current meters or acoustic Doppler devices are installed at varying depths for accurate measurement. Some also provide real-time data for accurate forecasting. Satellite data is also used to measure the discharge indirectly using satellite altimetry. Radar or laser altimeters, for example, in Sentinel-3 satellite, send a signal towards the water bodies and records its return time. This gives precise estimation of water elevation. Indian Space Research Organization or ISRO uses satellites like RISAT and Cartosat to estimate and forecast river flows. Discharge is more complex to measure because it depends on the estimation of both the cross-sectional area and average flow velocity. In large rivers such as the Ganga and Brahmaputra, the measurement is challenging due to wide channels, high sediment load, shifting river channel and high seasonal differences. Nevertheless, the discharge measurements are taken periodically for calibrating rating curves and validating models. Stage discharge relationship. Measuring continuous discharge data is impractical due to cost of instruments and field studies. To bridge this gap, hydrologists develop a stage discharge relationship at a known place. Both stage and discharge are measured for some time and an empirical relationship links observed stage values to corresponding discharge measurements. This is commonly known as a rating curve. This equation is often a power function expressed as Q is equal to C H plus A raised power n, where Q is discharge against any given stage H and C, A and n are empirical constants. Over long periods, the equation is established and used to convert stage data into a continuous discharge record. It assumes that the channel morphology remains stable over time at the control section. Now, Manning's equation. In some cases, measuring the velocity at a river is always not possible. To address this, a theoretical relationship between channel characteristics and average velocity and discharge is used. It relates velocity to channel roughness, hydraulic radius and slope. This is called as Manning's equation and is expressed as V is equal to 1 by n multiplied by R into 2 by 3 into S 1 by 2 or Q is equal to A into 1 by n into R 2 by 3 into S 1 by 2, where V is the average velocity of flow in meters per second, R is the hydraulic radius in meters and S is the slope which is dimensionless. The Manning's roughness coefficient n depends on the characteristics such as sediments, vegetation and sinuosity. While the rating curve is empirical, Manning's equation is a theoretical concept for estimating discharge in ungauged rivers. Now, how discharge data is important and what is its significance? Discharge data serves as the vital quantitative record of a river's flow behavior. It acts as the fundamental hydrological parameter that is used to understand the real conditions and the theoretical hydrology of a watershed. The observations are particularly critical to track flood peaks, issue early warnings, and assess long-term flow trends under climate variability. The data becomes a backbone of water resource planning and management. Discharge data is a variable used to develop, calibrate and validate rainfall runoff models. This allows the hydrologists to imitate the catchment responses under varying climatic and anthropogenic scenarios. The time series discharge data help us to understand the seasonal and annual water abundance or scarcity. For river interlinking projects like in Seine Betwa, Kaveri, Krishna and Godavari basins, it helps us to know how much and when the allocated water will be shared from water surplus to water scarce basins. The discharge records are critical for the design and safety of dams, bridges and other infrastructure. The long-term data determines the spillway capacities of dams such as the Bakra and Hirakud. For this, frequency analysis is carried out using models. This is important to safeguard downstream population from catastrophic failures and floods. Approximately 40 million hectares of land in India is prone to floods. Therefore, real-time discharge data is vital for flood forecasting and early warning systems in case of hydrological disasters. Long-term discharge trends are also a primary indicator of climate change. This is studied to reveal critical shifts and determine extreme events. Also, the continuous and accurate data is required for ecological studies and maintain water and food security. Despite having extensive monitoring stations in the country, there are several challenges to collect and model the discharge data, particularly in ungauged catchments. To address the data deficiency, hydrologists and government departments are increasingly employing satellite data, discharge morphology relationships or modeling techniques. The flow of fresh water from rivers into oceans is also measured to understand the ocean processes like salinity, sediment flow and pollution. Now, let us discuss modeling discharge and hydraulic hazards. Modeling the discharge and hydrological variability is vital for hazard mitigation. The scientific analysis of how rainfall produces stream flow and how much is crucial for quantifying water availability and mitigating floods, droughts and water scarcity. This is particularly important in watersheds where monsoon is becoming erratic and human impacts are increasing. Scientists are using several methods to measure and understand this variability in river discharge. The models vary from simple empirical to complex mathematical models. These models like soil and water assessment tool are widely used to understand the complex catchment dynamics. The Central Water Commission has installed discharge gauges across the country and utilizes models for real-time flood and drought forecasting. In rivers like the Brahmaputra and Mahanadi, models show that the flow has highly changed to critical levels. Models like Hydrologic Engineering Center Hydrologic Modeling System mainly predicts peak flood discharges, while as SWAT is applied in the semi-arid watersheds for soil moisture, floods and drought management. Another method for modeling the direct runoff responses from rainfall excess is the unit hydrograph theory. It is a vital technique for predicting monsoon-driven runoff and flood. Similarly, the Soil Conservation Service curve number method is extensively applied to quantify runoff volume. It is based on soil type, land use and antecedent moisture conditions. The need for robust modeling was felt during the devastating floods of Uttarakhand in 2013 and Kashmir in 2014. In these fragile Himalayan basins, models take into account the steep slope, glacial melt and anthropogenic changes. This helps to explain how rivers flow under different scenarios of climate change and human effects. Similarly, in urban basins, the hydraulic models map flood inundation risks and guide in designing drainage systems to withstand high intensity rainfall events. However, the modeling methods face challenges despite their usefulness. Models demand huge data which is very scarce in several catchments. To address this, satellite data on rainfall and other processes is used. By integrating discharge models with climate change projections allows planners to estimate the return period of future floods and droughts and ensure dam safety. Now let us discuss river discharge variability in India. A reliable and predictable river discharge is vital for water modeling, safe utilization and national water security. However, river discharge across the catchments in India has become highly variable in the past decades. The unpredictable flow has made the hydrological processes very volatile. There are multiple reasons for this shift in flow and include climate change and anthropogenic interventions in the catchments. This is causing floods, droughts and threatens water security from time to time in the country. Therefore, understanding the dynamics and variability is critical for future sustainable water use. The primary driver of the intense river flows is the change of the Indian summer monsoon. The southwest monsoon delivers approximately 75% of the annual rainfall in just 4 months. As per the Indian Institute of Tropical Meteorology, an increase of about 75% in severe rainfall incidents is seen between 1950 and 2022 in parts of central India. Although the overall yearly rainfall has remained more or less uniform, but the temporal distribution has secured. The number of moderate rain days has decreased and high intensity events have increased. The runoff has become saturation excess in some areas and infiltration excess in others. Some rivers are showing flasher hydrographs with higher peak discharges. The reduced rainfall also impacts infiltration and has reduced groundwater recharge and base flow component of the hydrographs. Similar variability is seen in the river flow of the Himalayan and mountain watersheds. The change of precipitation pattern, reduction of snowfall and increase of rain events in the Himalayas is seen. Cryosphere, that is glaciers and permafrost, is losing. Studies show that about 15% glaciers in the Himalayas have vanished in the past decades. The snow and glacier melt in these catchments contributes to about 40 to 50% of annual flow. Therefore, warming and human impacts have caused a reduction of the meltwater and reduced the peak discharge earlier in the summer months. In some watersheds, the streams become dry in warmer years. During the Uttarakhand floods of 2013, the Mandakini river was flowing with exceptionally very high peak discharge of more than 4,000 cubic meters per second. This was 3 times more than the normal flow in the river. This flow devastated downstream homes and infrastructure and took human lives. Conversely, the flow in the peninsular rivers such as Godavari, Krishna and Kaveri also show variable flow patterns. The major reason is a reduction of monsoon rains and mainly the human interventions of storing water in reservoirs and interlinking projects. There are about 5,300 large dams in the country and 14% are in the southern parts. This has changed the natural flow regimes heavily in some catchments such as the Narmada, Banas, etc. Studies suggest that large scale river diversion projects have cut the annual discharge to the oceans by 20 to 30% compared to long term average flow. The Kaveri river has witnessed below average flow in over 30% of years since 2000. River flow has also tremendously changed due to urbanization. This is particularly increased the runoff coefficient across basins. This coefficient measures the fraction of rain that is converted to runoff. More the urban growth, more will be the runoff in a watershed. In some highly urbanized watersheds, the coefficient has increased by about 4 times. For example, in Chennai, over 80% of annual rainfall instantly converts to floods. Each year, such unstable river flows cause destruction of property, agriculture and take human lives in different states. Dear students, this was all about today's program. Hope you have enjoyed it well. Thank you for watching.